Alrighty, so second to last class. Thank you everyone for putting the assignments in. I'm grading as fast as I can. I will probably try to keep doing that during the weekend, so by Tuesday you should know where you were at, and I don't foresee problems, as the phrase goes. Famous last word. And so yeah, keep doing it, and then we can the class. We're nearly there. Well done, everybody. So well done, Wade, here in person, and well done, everybody online. So today I had promised that I was going to show you how I'm struggling with my own machine learning. And so we talked about support vector machines just a few weeks ago, or just a week ago. How to get a separation between the blue points and the green points. And I was thinking, like, well, I've been showing you this thing I've been doing, which is this morphology measures. Basically, it's a series of parameters, and I'm trying to figure out whether or not I can tell that some of them are undergoing a certain process, RAM pressure stripping, and the other ones aren't. And so this is kind of like an object lesson of the regularization parameter C, essentially how you penalize points that are going over the line that you're drawing. And so I'm drawing here, but of course, a very fancy way of saying it's a linear structure in multidimensional space. That's it. So here it's a two-dimensional space, and there's a line, and that separates out blue. And there's a couple of penalizers, points that are to become more or less slack with how much there's always a little, there's always with a Gaussian, and so all the values know all the other values. The other thing we can do how big the smoothing Gaussian, the smoothing kernel is. This is how big the Gaussian is. This is how, if it's not a Gaussian, maybe you have another function, right? So there's a second hyperparameter. So we have there's two knobs, we can turn on. Same idea, same algorithm, just two that we can tune. So already our parameter space is getting bigger. I haven't even touched class weight yet. I haven't gotten that far. It just took a while just to get here. So the wallaby, that's just a cute name by the Australians for their age. That their arch rivals, the South Africans, had cute as their so they went like, we're not going to be outdone. We have cute animals of our own. So wallaby was one of them, and so what I did was I have this catalog that I've made, and can I link it to RAM pressure stripping? This is basically the pictures blown up to scale for an enormous number of galaxies. Well, enormous number, I say, 150. And I have turned their appearances, like they look like little fuzzy things. They're small. The red one is like all plushy. And so I've turned that into. I also have an evaluation for all of them, whether or not they're undergoing a RAM. So the red ones are, we think they're having that effect. might show up of how they look. Is this actually blowing their head back? Yes or no. The blue ones are unperturbed, and so this is what you end up. So this is kind of like, okay, I have a feature space, which is all those morphology measures. So there's all like concentration, asymmetry, Gini, M20. They all have these fanciful names, but essentially it comes down, we've turned these really strange shapes into just a bunch of numbers, and that's our features. And we have a label. A label is, thankfully, yes or no. It's red or blue, right? So it's either red, it's undergoing ram pressure stripping, or blue, no, it isn't. There's no in between. I mean, you could think of it as like, well, this one's going through extreme ram pressure stripping, that one's a moderate, and that one's, none at all or hardly any. So you can sort of think of this as like ram pressure stripping could be like a sliding scale. But we're not doing that. We're just going with a label from yes and no. That's it, because it's an easier label to deal with. And honestly, this is hard enough as it is. So we'll just go with, I have red points and I have blue points. And here you can already see on any given pair, there's really no good line that I can draw to separate the two out, right? So I'm already in trouble. However, and so I have more of these parameters, right? I kept plotting more of this. So this is very typical of what you do before you invoke machine learning. The first thing you do is plot one thing against the other. Plot everything against everything. And so that's how you, that's where you, this value I, and I'm plotting it against M, and everything against everything else. That's what I'm trying to do. And so that's where I get started. And so we first build some intuition. Intuition is simply, I can't get away with just, I don't know, putting a cut somewhere. Like if I put a line somewhere, can I get away with that? Because if you can get away with that, then you're done in an afternoon. And you can say, well, everything above this line is ram pressure stripped, and everything below that line isn't. I'm done, right? Result, write it up, wonderful. Or if you've got something like this, that you could probably separate them out. I mean, the points here, for example, yeah, they're mixed together, but not 100%. So it's the kind of thing where you look at this and go like, well, the red ones are mostly over here, and the blue ones are mostly over here. I mean, they're really mixed, but over here they also look a little bit different. And here they look like the red ones over here and the blue ones maybe on the bottom. That kind of thing where you start convincing yourself that you've got something. If you're in that situation, you might go like, well, maybe I can maybe something's the thing that I'm trying to do. Your space, concentration, symmetry, Gini, M20, MI, and G, whatever they were, and R, everything that was in my catalog. I throw the kitchen sink thing and pull it up over. I have to go through just a whole bunch of iterations of this. By then, prune the features. So you start with all the features, and then you go like, working. What happens if I just want it to look good? So if you go back to here we go. You go up to it, which unfortunately I'm sure if you read it, I cannot read it, and I'm 2 paces away from it. Bunch of split on, and I realize that some of them are used more than others. So this is quite like, again, you learn more about your data. It's like, oh, hey, concentrations and Gini seem to be used a lot. And maybe that one, and something like M is never used. I never see anything split on M. So that's maybe useless, right? So maybe that's not next. It might be good for something else, but not here. And so you kind of get a feel and go like, G50 might, so these are 2 features. And here, I had 1, 7, 8 features. So 8 versus 2 is like, oh, suddenly I've made the problem a lot simpler. And then also the decision tree to go as deep. It does better, particularly because I took away some noise. Right, so great. Now remember that I was talking about support vector machines because I was still not. And I was wondering if I could do this with a support vector machine. Maybe I can do it better that way. And remember that we have that parameter C. That's one of the parameters. And so how much slack do I have to give it, right? So what I did, I remember the metrics that we have. We have precision, recall, and that F1, which is a mix between precision and recall. Those are 3 metrics. And so I can see, as a function of C, how well, for this particular feature space, I split the sample, right? So I split the whole sample into training and test. I trained the support vector machine on one. I tested on the other. And then I do, so let's do case of C. So the C, like, I'm allowing more and more. And so sort of weirdly, there's a peak at the beginning, which I have no idea what's happening there. But then there's like around 5, it seems to sort of does its best job with both recall and precision, because you kind of want it both to be good, right? So this first weird jump is probably something to do with the small sample, but I'm not quite figured that out. But at 5, that seems to be peaking out. So that's for that feature space. And I can do it for the other ones as well. So here's my Genie R50, and I do mid R50 and symmetry and Genie and R50, and then everything combined. And I can sort of see what value of C seems to be working best. And so it seems to be 5. 5 seems to be working well for precision and does a good job with the recall. Now, the thing that I want you to notice is that all of them seem to go to about 40%. Now, that's not great. That's essentially worse than flipping a coin. So that's where I'm at right now. But it's the kind of thing that's like, this is how you get started with deciding where to go with machine learning and seeing if you can do a better job. Now, this is the other version of this, where you go through all, and remember, you have that other hyperparameter, which is the kernel, like basically the level of convolution that between your feature space and where you want to end up. And so you run through a whole series of them and see where the accuracy is better. And you kind of see, like, yeah, they're all kind of the same. They're not much better. This is the another version of that. And so I've run through various feature spaces and various sets of settings for the support vector machine. This is what I was doing yesterday. And you can sort of see that they seem to climb to close to where they peak out anyway. So it's really not a big difference. And so, I'm sorry, and the trick that they showed me was, and this is still ugly, so we'll go with this one, is that you've got red points and blue points, and then this is sort of like in part of the feature space. So let's say M and I. They plot M against I, and here's a bunch of different values of gamma and C, and how good does it color the blue around the blue points and the red around the red. So you have a bit of a feel for, like, okay, this seems to be doing okay. Or, you know, it's just sort of doing terrible everywhere, or equally terrible everywhere. So that's the kind of thing I'm doing right now. I was going to show you my work because you have been showing me my work for the last few months, and I'm very happy with that, but this is where I am stuck at the moment, trying to hyperparameters for a support vector machine so I can see if I can classify this way or not. The answer so far, so, right, I have many values of C. I can try each feature, and also many values of gamma I can try. Or I'll go to Gaussian, or I'll go to something else. And honestly, there's a lot of dead ends. So it gives you an idea of where I'm at. I just wanted to report in. And so if there are any questions, I am super happy to start answering them. Maybe go through an assignment if you are stuck on something. But I have noticed that everybody has been hard at work, been putting the assignments in. if you, and I already have the first term in, so, now, when you want to do that, my screen burn. So, can I help you with something? Yes. Okay, cool. Start with that.
Calculate the chi-square value that fits the data. So I did that in a
Okay, go up a little bit. This is the 3 data sets, the 4 data sets, right? Yeah. Yeah. So this is exercise 3. Exercise 3 has 4 data sets that have super engineered to be super sneaky. They all have the same variance and mean. They all have the same standard deviation if you fit a straight line through it. Because a standard deviation is a reduction of the information that you want. It's the sum of all the differences, but it doesn't say where the biggest difference was. So if you fit a line through it, and for example, there's a bunch where they all have the same, like one of them is just, they all have the same x value, and then there's a range of y values, and then one outlier all the way out. And because chi-square can't tell where the big difference was, you fit the exact same slope and intercept at that, and have the same chi-square. This is why chi-squared alone, it was perfectly fine how it was. Why was this mean? This wasn't mean. This is the thing to warn you against, to not just use chi-squared as the single evaluator for how good your fit is, how good your model did. Because if you don't show the data at the same, you could get hoodwinkled, right? That's the whole point of those four data sets. They look exactly the same in the evaluation numbers, yet clearly one is a good line, one is a line with an outlier, and 2 of them aren't even lines, right? So 2 of them have the wrong model. One of them has been completely skewed by an outlier, and only one of them is a case of a good chi-square fit of a line to data. So always plot your result next to doing a chi-squared. And there is a particular piece of astronomy software that gleefully reports the chi-squared, and I've seen many people just make their decisions based on just that number. And this should kind of convince you to not do that, and to just also go back to like, well, what's the residual? What's left afterwards? So if you can get a visual of the residual, if you can plot the residual, you subtract your model from your data. Does it look, like normal noise, or does it go like this? Is it like is it shaped? Is it the same across my x bar, or is it, does it go? Is there still a trend visible? And if there's still a trend visible, it's like maybe my model wasn't a good description then. Like that's, chi-squared alone will not tell you that. That's the entire reason of the exercise. That's it. Okay. Make you nice and cynical for the chi-square. Good. All right. Can I help you? Can I help anybody online in exercise? Dead silence. Okay, cool. Well, that's easy peasy. All right. I just wanted to give you a status update where I was, and help anybody with any outstanding at any point or any assignment. Help you on Tuesday. You're doing so much. Okay. Oh. And it's just me now. All right. Gotcha. I don't have to, but yeah, happy to. I'll. Assignment 6. All right. Well, make sure that you always send in what you have, because might be enough
I didn't
there.
know much of anything because I
Okay.
got stuck on like one of the first exercises.
Okay.
What was it? So this is the Kolmogorov, Smirnov, and Anderson-Darling.
Yep.
And I think I was.
How do you the KS test does? So you can either do two. So KS test, there's two functions that do the KS. The first one is, I mean, I think it's called KS test. I mean, you import it as KS test. That expects one distribution of data, one array of data in one-dimensional. And then the second thing is you specify what kind of distribution you're comparing against. So you can say, you'll have to look up, I mean, some of these are just made to make you to go like, all right, I'm importing this thing. That means there is also a man page, there is a manual page, there's a reference page there, so I can Google Python KS test. And maybe, you know, you glance over SciPy or something, and it'll be the first thing, it'll be on the first page of Google. And so you can look at that there's, apart from it expects a function, there's a couple of other parameters, and one of them is, I think that's CDF or something like that. It says, yeah, I'm expecting the normal distribution or Gaussian, or I don't know, there'll be a couple of options, and you try one of those options and see what gets out.
Okay. So it's not that I'm defining.
You can. So here's the beauty.
What I did here, I just ran it. This kind of worked. And gave me a p-value of 0.
Okay. So statistic is the KS value, so it's the biggest piece of daylight between the two of the distributions if you plot them cumulatively. KS test of 1 means 100% difference between both, and a p-value of 0 is, you know, infinitely small. It's a little alarm bell should probably go off.
Right. That's.
Percent difference never happens unless. The difference. Really, look at the KS test, just KS test, not KS underscore 2samp, because KS underscore 2samp actually compares one distribution two distributions that you have. So that's useful if you've got two sets of values that should be the same, but are coming from two origins, for example. You want to make sure that they have been drawn from the same parent distribution, so you compare the two of them. If you go like, well, this should be a log normal, or this should be a Gaussian, you take your data that you have and say, compare that against the log, or like they have a couple there. If it isn't there, you define it yourself with, you know, infinitely large, like 10,000 samples, but only if it's not defined as a function in the KS test. That's what I would recommend.
So is that wrong then, considering those values I'm getting?
So let's see, what are we doing? So we need to go look at KS test. Do you have it up somewhere?
You want the actual documentation?
Yeah. Because that's,
Is it SciPy?
yeah,
Okay.
that's it. So it asks for two, like RVS is the array. That's our data. CVS is a string that says what it's expecting, and it should be name of distribution in SciPy stats, and there'll be an example here. So norm, for example, is the normal distribution. That's the Gaussian distribution. So that's the one thing to look for. There are others, and I'm trying to remember where if they had a little list here. No, they don't. So they go like, it's any of the SciPy stats distributions. Look at all the distributions that we can do. So you can basically say, I want to look at boy, exponential. I want to look at the Laplace or something like that, right? I'm comparing my data to that distribution. But it all has to be normalized. So if we're going back to here, we can say, so it's a, all right, let's see what it does now. That looks better, right? So that looks like it actually found something. And then we can also, just for sanity check, for example, you go like, did I get everything right? So you can do, excuse me, KS test, and you got your Gaussian distribution defined, and you say CDF equals norm. Those two should, as a string. And then suddenly you go like, oh, there is barely any daylight, but here's my p-value. Right? How many values? What's the length of the Gaussian again? Right? So you can go len Gaussian. Oh, print len Gaussian, of course. Okay, you got 7,000 in there. Oh, you wanted to say that the same length as the data. So that's. And the KS test says, but it's a pretty, is it significant? Would you say that is significant? Or is it, you know, the two of them are indistinguishable from, it's saying like, yeah, there's hardly any difference, but my p-value is incredibly high. So I'm not so sure if this is actually working. Oh, cool, you got the, so yeah, there's the CDF string, so that's what it's expecting. But this is why I always call it up on another tab, so I can actually click on it.
Yeah.
Just clicking through sometimes helps. And so, so you can do 2 times. This is the increase the sample size by a lot, 100 times the above sample for the Gaussian test distribution. So if you do this big Gaussian, you're now just multiplying everything by 100. And you want to have something that is 100 times bigger. So you want to take this and turn that, oh, sorry, so big Gaussian, I like the name, is simply 100 times, you sample it 100 times more. So it's a much bigger Gaussian. And so then you can test it again that way.
So what I did here is actually
multiply
increase
the Gaussian, every value of the in the Gaussian by 100. Yep, very easy to move that way. I think that should get you unstuck.